Welcome to Chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in Chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, on the sending side, on the sending host here, the transport layer segment is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram. And sometimes also called the IP datagram. Okay, so transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, in the packet header, in the IP datagram header, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in anime, so a packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up to the higher layer. Alright, so that is a general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, yes, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in canteen. Okay. Well, the thing you need to do first is this, routing. You pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take the high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus, or do we all rent a car or rent a number of these bikes so that we ride along all the way to canteen? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to canteen. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay, and that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end to end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now in this centralized approach, in the SDN, we actually ask a couple very powerful machines, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. Okay? So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. Okay? And it's very simple, very fast. Okay? All that is done is the packet coming in, the router look at the specific packet header field and match to an entry in the forwarding table. Okay, so this is called the fast output interface lookup. Okay, once we get a match, we get also the outgoing interface. Okay, let me illustrate. So these are the routers, okay, and inside the router, okay, you see this is the entire operating system stack. Okay. There's this thing called the forwarding table, and each router will have one of these. Okay. When there's a packet coming in like this, it's going to look into a packet header field, okay, and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. Okay, so output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. Okay, so this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here. Okay, higher up in the operating system stack. To be more exact, okay, and let's talk about the traditional approach first, where the computation is distributed. Okay, so the routing algorithm is going to be running on each of these routers, okay, and up here. Okay, the routing algorithm here, 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 and here. Okay, so each and every router, okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay. And this is the control plane. Okay. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here. Okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is going to provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers. Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out, and the data is just going to arrive. Okay. But unfortunately, yeah, the channel is not exactly reliable. Okay. And depending on how unreliable the channel is, the complexity, okay, of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay. So the service model we'll be talking about next is to talk about how we implement. Okay. What kind of channel we're providing here? Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay, and this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. Okay. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old, okay? But these are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay? And the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN ACK, and then ACK for the SYN ACK. Hey, that's establishing connection, right? It sounded very much like these, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So, just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers. Yeah, those are the major camps. But within each camp, you can probably define finer service models so that you provide different levels of service. So, for example, okay, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, okay? Or we restrict, okay, the time differences in between these packets when they arrive. So again, the service models, they can be finer, okay, or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time, okay, in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best effort. So essentially it's not guaranteeing anything, okay, no guarantee at all, okay, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, okay, between the TCP sender and receiver. Now ATM, okay, quite sophisticated, okay, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. Okay, so this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. Okay, so you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now, these two, however, okay, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. Okay. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee. And in this case, no longer a congestion signal going back to the data source. So you see, again, the network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever.